Doing Jack Black and Jason Monster. Winter is a really bad song. It's not good. Again. I mean, like at least like your photo like that might have 20 days, but it's fine.
Okay, so we're back at linear algebra again. And started vector spaces. We started speaking about linear subspaces. Which lecture are we at? Not writing it. Thomas, do you know what number lecture is this?
I think.
I think that's close enough. Lecture 8.
Okay. Last thing in lecture, you wrote all them on board. I love this thing. I was like in lecture 7. You only like
Great. Okay. So lecture 8, we talked about vector spaces over fields, which are sets of objects we call vectors, together with addition and multiplication by a scalar and some nice property. A subspace is a set, is a subset, and that is in itself a vector space with the same operations. So our first proposition would be, and I leave it for you as homework to prove it, given a vector space V over the field F. I'll remind you that the field is where the scalars come from. So given a vector space V over the field F, and given a subset U of V, then U is actually a subspace of V if and only if the following two conditions hold. First, the zero vector of V is contained within U. So any subspace must contain the zero vector in regular vector spaces in geometry, that's the axis point. The origin of the axis must be included in any subspace. 2, for every U and W, 2 vectors in U, and every scalar in F, it is true that U plus CW stays within U. And that is a shorthand which the first demand is that the set is not empty, because if it was empty, that this would be true in an empty sense, and we don't want that. We could just simply demand that the set is not empty, but it's easier to make sure the zero vector is there. And the second claim, make sure a closure will hold. And both closure for addition and scalar multiplication are rolled into one. Like I said, I leave it for you as homework to prove that this actually works. But it's very useful. We'll use it anyway. Yes, Thomas.
I mean, doesn't it, like from this idea just come that one of the dimensions must be 0 to be a subspace?
Why? If the entire space is 3-dimensional, the subspace could be 2-dimensional.
Yeah, but I mean, one of the like if we have a triplet, one of them should be 0 now. Or if every multiplication is on the field and it doesn't have all of the
No, no.
necessarily.
Example, no, not at all. Any straight line through the origin of the axis will be a subspace. Let me give you an example. And take U to be all of the vectors of the type A, such that A is a real number. That is a subspace. We will prove that is a subspace. How? Using the proposition. First of all, subspaces of what? Of R cubed, right? All the triplets. Right? First, and I'll make sure to write it. It's obviously a subset. Do you worry about that? These are some of the triplets. And the first thing we need to make sure it's the 0 vector is there. And obviously it is, right? If you choose A to be 0, then 0, 0, 0 is within that set. Next, given U and W within the subset and C scalar, we need to prove that U plus CW is within the subset. Okay? How do we prove that?
Because every U is just a multiplication of itself, kind of.
What is U? If U is within U, the U vector, right?
Yeah.
What does it equal to?
AA something.
So U is A, indeed. U is AAA. What is W? AAA times some constant. So B, right? Some other number. Read? Or possibly another number. Maybe W is also AA, but it's any B. So U, and I just say that the frame of the proving something is subspace is always the same. Let's say we're given two vectors from the subset, and we need to show their linear combination. Will define exactly what it means, but a linear combination is still remains within the subset. And the main thing to always do is, because vectors come from the subset, we can write them in a certain way, or we have a certain data upon them that helps us. In this case, we knew that all of the elements are the type a number, same number, the same number. So we need to change the letter because it mustn't be the same number. But still, when I write that U is AA and W is BBB, now it's easy to say that U plus CW is actually A plus CB, A plus CB, A plus CB. Agreed? And that is obviously within the set U by definition. It's the triplet of the same real number. So that is a subspace. Agreed? Another example. Given a matrix A, it's a rather important example. It's an example slash definition. Okay, so given a matrix A, which is of size M times N, define the null space of A to be all of the vectors from Fn such that A times V equals 0. All of the solutions, these are the solutions to the homogeneous system. Okay? So it's not completely new. We'll learn about system of equations. We're simply naming it as a vector space. But why is it an example and not just a definition? Because there is a claim here. This is indeed a vector subspace of Fn. And we'll prove it, right? But the null space of a matrix will be very important. After that, we'll learn about the column space of a matrix and the row space of a matrix. But for now, the one I can speak about currently is the null space, because we already learned about the system of equations. I just need to prove that it's indeed a subspace. I'll do it in 2 seconds. Tomas?
No, I was thinking about that. Why is it a subspace of Fn if we're multiplying by A? Like you say, yeah,
No, but you don't multiply by A. It's the vectors that when you multiply by A goes to 0. These are the solutions to the linear system of equations. It's either a plane or a straight line. These are these sets. And because we take a homogeneous linear system of equations, then 0 is a solution. The set of non-homogeneous system of equation is not a subspace because 0 is not there. If it was written here AV equals B, where B is not 0, then plugging 0 instead of V will not hold the system of equations. Okay? So the proof is rather easy. Proof, first of all, since A times 0 is 0, then the 0 vector is indeed within the null space. That's the first thing we need to prove. Next, given V1 and let's call them U, U1 and U2 within the null space, and C within the field, the scalar field, we need to prove that U1 plus C U2 is within what?
Within NA.
Exactly, the null space of A. Agreed? So what is the next step? You see the frame is the same as before. I've shown that the 0 vector is there. I'm taking 2 arbitrary vectors and an arbitrary scalar. And I wish to show that the linear combination is still there. So what is the next step? Do you remember? Yes?
Because it's an homogeneous system, summing whatever two homogeneous systems will give you an homogeneous
That's
system.
true, but I want to prove it.
Ah,
So what is the next step? And I'll remind you. I said, first I'm saying given, then I need to think what does this data tells us. Here, having the fact that U is within U, it meant that U is of the type AAA. So do it again here. You know that U1 is within the null space. What does it tells you about U1? That
Zero.
A times U1 is 0, right? We know that A times U1, U1, is 0, and A times U2 also 0. What do we need to prove?
that A times U plus CU2 equals 0.
Exactly. So that's a translation of what we have and what we need to prove to be specific to that example. Indeed, and then the proof comes, and the proof is so easy. Why? Because we learn about algebra of matrices. A times U1 plus C U2 equals A U1 plus C A U2, which is 0 plus 0, which is 0. Okay. Any questions so far? Okay. Another example. Take U to be all the functions f of x within, tell me if you learned this in discrete mathematics. I have all the function from R to R. I think that's an easier notation. Okay, I'm taking all the function or from R to R such that f of 1 equals 0. Is that a subspace? So you might ask me a subspace of what big space? And note the set of how do you note the set of all functions from R to R? How I wish to use it. Did you learn it in discrete mathematics?
If the 2 points are 9R.
That's one function.
How
do you note the set of all functions?
R to the R.
Yes, exactly. Double R to DR. Right, that makes sense. That's the set. I'll write it in words as well. The set of all functions from the reals to the reals is a vector space. You can sum up 2 vectors, you can multiply by a scalar, so it's a vector space, right? It's the generalization of what I told you last time with the one of the times with right? A sound is basically a function, right? So it has a connection with that. In any case, I'm asking whether so is U a subspace of V? Is the set of functions that equal to 0 at the point 1 a subspace of all the functions? So let us make sure. What is the 0 function? What is the 0 vector here?
Let's just see.
Yeah, is the constant 0 function where everything goes to 0. Every other function that you add to it, it won't change it at all, right? Is this function within U?
Yeah,
Yeah, because the 0 function sends 1 to 0, and therefore is a part of U. So that's always the first thing. Make sure the 0 vector is within the subset. In order for it to be a subspace, we need a 0 vector here. And that happened in this case. Now, what do we do next? We take two vectors within the set. So F and G within U. And we take a scalar within the field, which is R. We need to prove that F plus CG stays within U. So what is the data? What do we know? If F and G are within U, what can we say about them?
that they are a function of one. No, that they're a function whose function 1 equals 0. I mean,
Whose function one?
whose we interpret 1 as 0.
We send 1 to 0. Yeah, we know that F of 1 equals G of 1, and they're both equal to 0. Agreed? So what happens if we plug in 1 into F plus CG? We get F of 1 plus C times G of 1, which is 0. And thus did F plus CG is within U. It is a subset.
I mean, is it really that simple? Because
Yes. Yes, it is that simple. It's linear algebra. It's supposed to be uncomplicated algebra. What's hard about the course is getting all the different definitions and it's a whole new language and connecting it to what you know about geometry and understanding that it happens in other dimensions or vector spaces or whatever. But yeah, the arguments are usually simple, unlike calculus. In calculus, there are more the claims are more intuitive, but it's hard to prove them. In algebra, we have no idea what we're doing, but it's easy to do. And that's the difference between the two courses.
yeah, I just mean, is it this difficult to prove because it's from R to R, it's complete, and you just say for every other part of
No, I think it's easy because it's 0. If here that number does not matter at all, and this must be 0 because 0 has the unique property that when multiplied by anything, it's 0, and when you add it to another 0, you remain with 0. If it was f of 1 equals 2, then it wasn't a subspace. By the very start, the 0 function was not there, right? And it also wasn't closed under addition and multiplication by scalar. So I think it's so simple, A, because it's true, and B because it is equal to 0, but any other number, it wasn't true and wasn't simple. Okay, it's kind of like the same thing. Why am I saying it's kind of like the same thing? No, it's not exactly that, because I didn't take all the vectors that go to 0, but I took all functions that send a certain vector to 0. So it's not the same thing, but it's kind of similar because matrices are functions.
So,
But given a certain function, taking, oh, but it's not linear function, whatever. What I wanted to say was whatever.
so the proof strategy is first we find the zero element and then we try to show the two different vectors.
Yeah,
That's
I did it 3 times.
Yeah,
Strategy is to follow
what you said.
what I said 3 times, yeah. And to add more for the joke, strategy is follow the proposition. That's exactly what the proposition says.
No, yeah,
The
no.
strategy is do it.
No, I understand. Like the second part is always trying to show the zero vector because it's the easier one, or
No, that's different.
no. You show like in both cases or all three cases you
I did 1 and 2. I showed the 0 vector is there, and then I showed for every u and w and c, u plus cw is in there.
but on the second or the third one it wasn't the zero vector now.
It was. This is the 0 vector here.
Yeah. No, the second part, not the first one. Like the first part you showed there is a zero vector.
Yeah.
On the first example, you showed something different.
No, I always showed 0. That's
Yeah, no,
the first
yeah.
example.
And then on the second
And
part,
the second part, you don't show 0. On the second part, you take 2 arbitrary vectors, always. You
okay.
show 0 and 2 arbitrary. Look here, 0 and 2 arbitrary.
Mhm.
0 and 2 arbitrary.
So it's
Always. That's the frame. That's the method. Okay. Now next. Question. Is the union of subspaces a subspace?
not necessarily,
Why?
because you can get two subspaces that if their union just make the whole space kind of thing.
If it makes the whole space, it's definitely a subspace. Right? Subset or equal.
Problem is, if there's a disconnect between the addition of.
Could there be a disconnect between 2 subspaces? What is the intersection of 2 subspaces? Who is always in the intersection of 2 subspaces?
The zero.
The 0. So it's going to be disconnected. So let's look at the following example. Let's take U to be all of the vectors of the type AA such that A is a real number. And W is all of the vectors of the type A minus A such that A is a real number. U and W are subspaces. I'm telling you that without proof. And these are indeed subspaces. Both U and W are subspaces of R2. But about the union union W. That is subspace.
I mean, I'm thinking that the sum of vectors from U and W will never give you the zero vector. I accept if they're both zero. That might be a problem.
What's the problem?
Like if you have a like two from U, you can't have -2 -2 from W, and the sum will never be zero.
Why would it never be zero? It will be, it won't be zero, okay. So you say, 2 does not have a zero within, W.
I mean,
But
it
it
has,
does, an inverse, but it does have a negative, -2, it's within U.
Mm.
Don't have to say that the negative is on the other line, it's actually obviously not there, right? Because every subspace has a closure, so it has its negative vector within it. But what is the sum of 2 and 2 minus 2?
for 0,
And what can you say about 4, 0?
that it's in neither of them.
So what does it mean?
There's, if it's the second,
There is no closure. There is no closure. 2, 2 and 2 minus 2 are within the union. Yet their sum is not within the union. Yet, yet 2, 2 plus 2 minus 2 is 4, 0, which is not in the union. So it's not a vector space. Right? A vector space must be a vector. A subspace must be a vector space. A vector space must have closure. So this is not a vector space. Right? The union is actually homework again. Prove that the union is a subspace if and only if U is contained within W or vice versa, or W contained within. It means that the union is only a subspace if the union is actually one of the original subspace. In any other case, it's definitely not a subspace. I think it's a very good exercise to do. I don't know if Mir would do it. I have it on my videos on linear algebra, but it's a. I think it helps to understand subspaces to do it. Okay. What about the intersection of two subspaces? What is the intersection of two planes, for example?
line,
A line, which is also a space, right? So, proposition given a vector space V over the field F. Stop going back to Hebrew. Given a vector space V over the field F, and given two subspaces U and W of V, then their intersection is most definitely subspace. So the intersection of linear spaces is indeed a linear subspace. And let's prove it. Thomas, what should we do in order to prove that the intersection is a subspace?
the 0 element.
Yes, is the zero element within the intersection?
Yeah, there
Why?
for it to be a vector space,
Yeah.
there is a 0 element, therefore.
Since these are vector subspaces, each of them contains the zero vector. Therefore, the zero vector is contained within the intersection. What's next?
Arbitrary vectors should be
Given V1 and V2, two arbitrary vectors of the intersection. And the scalar C from the field. Need to prove that their linear combination V1 plus CV2 is also within the intersection. Why does it work?
because for them to be in the intersection, they have to be in one in the
Yeah. V1 and V2 and U, which is a subspace, and therefore their combination is also within U. Similarly, V1 and V2 are both in W. And that's, by the way, here you see in a good way why does it not work for the union? Because if V1 and V2 were from the union, then one of them could be from U and the other from W, and then I have nothing to say about their sum. But within intersection, it works perfectly, and therefore, and thus, and V1 plus C V2 is within the intersection. Any question up until now? So what do we do since we don't have union? If we have two lines, their union is an X mark. You see what I mean? If you just take two lines, the union is just the X. It's not what you want. What space can be created from these two lines?
not space. Like
No, I mean, what space is created from? You have one axis and another axis. What are the two? What can you create from these two axes? A two-dimensional space, a plane, right? So I wish to talk about the plane. Union was the first thought because I'm saying I'm taking everything from here and everything from here and throw it together. But the union does not have closure. So what do we do about it? We define the addition operation between subspaces. Definition for any two sets, not just subspaces, A and B, within some vector space, we define A plus B be all of the A plus B's such that A is from A and B is from B. Okay. And homework proved that if U and W are subspaces of V, then their sum, the addition of U and W, is also a subspace of V. Because I'm able to sum, I'm adding the sum of every two vectors into the set, I get the closure, and that is actually a subset. I told you as homework to prove that it's indeed a subspace. It's not very hard. I wish to give you an example. Take U to be all of the elements of the type A, comma 0, such that A is a real number. And W would be all the vectors of the type 0, comma A, such that A is a real number. Then what is U plus W? Can you guess? So you don't have to guess. What is U plus W?
A.
So I'm glad that you gave that answer, even though it's the wrong answer. So is it all AA?
No, because it needs to be C.
Because you summed up A0 and 0A. But do I have to sum 1, 0 only with 0, 1? No, the definition says sum up anyone from the first set with anyone you like with the second set. So the correct thing to do, it's right, it's all of the A0 plus 0 B,
Sure.
right? That's a thing where A and B are real numbers. You see why? Because I'm taking an arbitrary element here and an arbitrary element here, and I sum them up, not necessarily using the same letter. And I say I'm glad, because that's the first confusion students usually have when they see this example. If you think of it geometrically, I think it would be clear, right? What is A0? It's the x-axis. What is 0A? The y-axis. What is the sum of these two? It's not just the line in 45 degrees, it's the whole plane. And that's exactly what happens here, because what is A0 plus 0B? It's all the AB such that A and B are real. And in other words, it's R squared, it's the whole plane. And so that definition really did what I wished for it to do. It gave me the subspace that is created from these two subspaces. It's actually the least subspace that's created from them both, because all I demand is closure. I'm taking the elements from A and the elements from B. In order to contain them both, I must contain their addition. And then it's enough to be a subspace, but it's the least one. Any questions so far?
I mean, for a full proof, we need to prove the zero
A full
element
proof of what?
of this example.
The example, it's foolproof, because it's used the trick, because A0 and 0B happens to be AB, which we know is R squared. It would have been a bit more complicated if I'll take, for example, AA here. I'll give you that for homework. Homework that all of the, I'll write it in short, AA plus all of the A minus A is also R squared. So I'll tell you that you can use by-sided inclusion. You can show that the right-hand side is included within the left, and the left-hand side is included within the right. But it's a bit of a waste of time, because we will have better tools for that in the future. Okay, so it's a good exercise for now, but in the future we will have a very a simple reason for why is it true, and it will has to do with dimension. We'll be able to say that these are two-dimensional subspaces of the same space, then therefore they must be equal. But it will take us a few lessons until we learn about dimension and able to use them. What? Ah.
My husband.
Always.
Harmonic, it's harmonic.
That's home.
Right.
Yeah, no, you're right. Home work. I wondered if I always wrote HM. Work.
I don't think so, but.
It could be,
I just-
yes. And M is for home. We had a joke the other day, do you know about the concept of STEM subjects?
The
So what is
science,
STEM? Science,
technology,
engineering,
engineering, math.
and M. Yes,
Okay.
because in Bar Ilan they say and medicine, and then they completely ignored us, which was annoying. Yes. And the other one, which everyone hates.
Physics.
Yeah, no, no, I think physics is within science.
Say that math is also inside.
Yeah, but also technology and engineering, right? Yeah, I agree, but it was just a joke, but it's funny because it's true. Every time they pour money into the departments, they say computer science, obviously, engineering, yes, it's important, math.
Are we going to put, are we going to?
Do we actually use it?
Do we need to put money on Mordor kind of
Yeah,
thing?
yeah, more, yeah, yes. I see in my Palantir that you're going to fail the final, I think, burning class. Okay. So, these were all rather technical but important. We need to do intersection of subspace and addition of subspaces and talk about it. And what next? I will open the wiki to make sure that I didn't forget anything. We did that section, but the next main subject is to talk about dimension, but it will take some time to get to speak about dimension. We need to speak about a few things first, but let me just make sure that I didn't forget anything from this. So we have vector spaces. And this is a nice piece for homework that a scalar time a vector will be the zero vector if and only if either the scalar is zero or the vector is zero, and -1 times u is minus u. These are nice homework exercises. Null space, yes, and addition. And this I'm going to skip. Am I? Let me think about it for 2 seconds. I'll tell you why, and I'm not sure if I'm skipping it or not, but I did forget that. The next is the dimension. Yeah, so that's what I forget. I'm happy that I opened it, and I'll tell you what the thing is. Direct sum, סכום ישר, of subspaces is usually being taught in linear 1, but used in linear 2. So there's both a reason to teach it and not to teach it, because if you don't have it in linear 2, you will have a problem. But it's always not fun to teach something that you don't understand. Why are we so obsessed with it? And in linear 2 is actually rather important. So usually in linear 2, they do it again. So what I will do, I will speak about it not for too long. That's what I will do. I will speak about it, but I will try to contain myself. Okay. Definition. Given a vector space V and two subspaces. Subspace U, U and W. We say that U, oops, not belong to the vector, belong to the subspace, to the vector space. We say that the direct sum of U and W equals V. Are you, by the way, before you're leaving, are you in linear 2 this semester?
Not this semester.
Oh, okay.
Excellent.
Yeah, I will be with everyone next semester.
Yeah, no, I just wondered if you were, I wanted to ask you if you saw it already, but never mind.
Well, I did linear one in a math program.
Yeah.
We-
No, but my point is whether in linear 2 you see it or not, but it doesn't really matter.
I can check.
Yes, yes. And we say that then we say direct sum, we read it direct sum if the two following conditions hold. The first one I think is quite obvious. We wish U and W, the sum of U and W, to actually be equal to V. But we, on top of that, the circle here says another thing, that the intersection of U and W, what do you suppose, what do you guess it will be?
I saw it.
Yeah, it will be only the zero vector.
And that's the reason they use the XOR sign.
No, I think it's plus with the circle. So plus is obvious and the circle means zero. So it's addition.
I mean, usually that's the same reason why it's in XOR, but it's because it's exclusive to something.
No, but I don't think so. Because in union we have something similar. The union of the sets is called direct, their intersection is empty. And then you say you put the union sign and add a circle. So I think it comes from that. In any case, it basically means these are two different spaces that have nothing in common. So you will see the dimensions will be the number of directions you have. So this says there is no joint directions for them both, and the dimension will be the sum of the dimensions. You will see that. That's just the definition. So what can we do about it? I can leave it just like that. I don't wish to. You showed me today that in your homework you had to, and I'll give you that as homework, show that, first of all, the set of all symmetric matrices, right? Where is the matrix within double F n on n? So show that this is a subspace of all the matrices. That's one. Second, show that the subspace of all antisymmetric matrices is also a subspace.
I mean, it's not vectors anymore, is it?
It is. This is a vector space. Why? There is addition, scalar multiplication, and all the properties. This is indeed a vector space. Okay. So show, I will emphasize it by calling it P. Now it's definitely a vector. Okay.
No, I mean, but
It is a vector space.
a matrix is a.
The set of all matrices is a vector space. and a matrix is a vector. Algebraically, not geometrically, right? That's the whole point. I'm so confused as to why you are raising it now when you accepted without arguing that the functions are vectors. The matrix is a specific type of function, right? But functions altogether were a vector. You can add two matrices, you can sum them up by a scalar multiplication, and all the rules apply, all the nice properties. So it is a vector space. You need to prove that this is a subspace. Actually, in order to prove that this is a subspace, you don't actually even have to understand it's a space. You just say, is zero a symmetric matrix? The zero matrix is a symmetric? Yes. Is the sum of and the combination of two symmetric matrices also symmetric? Yes, obviously, yes.
I mean, I think the most confusing part is the naming, nothing else.
Yeah, I agree. But that's a big point in this class. You remember when I said we had geometry, then we had algebra that helped us solve geometric problems, and now algebra became a whole monster of itself, and we identify these algebraic structures in other places as well, and we still call them vectors because it's vector space, but they are vector spaces algebraically speaking, not geometrically speaking. I cannot tell you for the life of me, if you give me a matrix, what is its direction, right, or length. I could algebraically compute the length actually in under some definitions of x that's linear too. But direction, I really think I can not give it. In any case, show that U is a subspace. Show that W is subspace, and let me just write in words. Show that these are subspaces, and next, show that U plus that the direct sum of U and W is all of the matrices. You basically had the main thing you need to do here. Wait, something important, not when one of the field plus one of the field, almost forgot about it, is not a zero field. If you take a field where 1 plus 1 is 0, it's actually not true. A matrix could be both symmetric and anti-symmetric other than 0. But if 1 plus 1 is not 0, then this is a direct sum. And what I started to say is that you showed me that within the homework that you had to prove that each matrix is the sum of a symmetric and an anti-symmetric one. That's the main thing you need here in order to prove that the addition is the whole set of matrices. So this is a nice example for homework, okay? Another theorem, and we'll decide together if I'll prove it fully, but at least I wish you to understand it. And before I'll state it, I give you a short introduction to it. Say introduction to the next statement. It's one of the main reasons to use direct sums. Any of you learned some physics? You did, right? And you regretted it, right? Or not? Did you start physics last year?
I went to 2 lectures.
Yeah, okay, yeah.
I had it in high school and I regret it every day.
Okay, great.
I
And so,
went to an engineering profile.
oh, I see. So in any case, it's not really hard physics. Say you have a slope and you have a car friction. You have a car rolling down the slope. What are the forces being applied on the car? So one of them is friction. Assume there is no friction. It's on by points. Gravity, right? So gravity is in this direction. Agreed? We wish to understand what is gravity doing to the car. So what we actually doing, we separate the gravity into two parts. What was the name for the parts? We said it last time.
Normal and
רכיבים, no, in general. Two
components.
components, thank you. It's two components. My drawing is perfect, if that's what you wish to say.
Gravity is always done. The reason it's going left is because
Gravity, and that's again, that's what Newton did. He said, we talked about it last time, the other way around. What do I mean? I told you if someone applied pressures or force in this direction and someone else applies force in this direction, if you sum these two vectors, you get the שקול הכוחות, anyone know say?
Equality between the forces.
No, that's the literal translation. You get a force which represents all forces. I'm sure there is a word in English. Resulting force? Maybe, whatever. In Hebrew, we say שקול הכוחות, which is shiklul, it's everything together. In any case, you can represent both forces together by one force, by one vector, right? That's what Newton said in his first corollary from his three laws. What we're doing now, it's the opposite. We have the so-called united force, and we wish to separate it into components. Why would we go and do that? Because gravity does two separate things. One of them is pulling the car down, and the other one is forcing it into the slope, right? Which causes the normal force and then causes friction and whatnot. But if I want to know how great is the force in that direction, obviously it has to do with the slope, right? But I need to separate the gravity into two components. Agreed? Now, an important question is there only one way to do it or more? Think of how horrible the result would have been. Maybe it's the sum of these two components, and that will be the speed down the slope. Or maybe these two components, right? Maybe it's also the sum of these two components. Could it be? And then the speed will be different, and the speed will be chosen randomly between different ways to factor the force into two components. It's absurd. Do you agree? So the theorem says that when you have a direct sum, you have a unique way to separate into components. Okay? So in physics, you don't actually have to say it's a direct sum because it's so easy to I don't know. They do it usually, they're using the sine or cosine of the slope, right? It's a shorthand. But the other idea, which is very important, like with sounds, is there only one way to separate the sound you hear into components of different frequencies. The general proof, direct sum, is there is a unique way. It couldn't be that the E and C sounds would be the same, the exact same sound as G and B. Okay, couldn't possibly be. There is a unique factorization to components. Okay, and so we expect a unique factorization of the force to components. We'll say the blue ones. Okay, so that's what the introduction, and I will say the theorem. assume that the direct sum of U and W is V. Not assume, that's if and only, sorry. Given a vector space V and U, trying to write lesson. Okay, given a vector space V over the field, not sure I need the field, whatever, over the field F, and given U and W subspaces of V, then their direct sum is V if and only if for every vector in the vector space there is a unique pair of components UW in U cross W. That's from discrete mathematics. That's the set of pairs, okay? Such that V is U plus W. Such that V is U plus W. Okay, so direct sum promises us unique factorization into components. In linear 2, it's important. And linear 1, it's important to questions about direct sums, which is a bit self-referencing. Let's prove it. Proof. First, assume that the direct sum, U plus W is the direct sum. Okay? Then, for every V in V, there must be U in U and W in W such that V equals U plus W, since U plus W equals V. That's by the definition of a direct sum. I'll remind you, direct sum, we say that the U direct sum W equals V. If U plus W is V, and also the intersection is only 0. So I know that U plus W is V. So everything is V is also in U plus W. So there are such U and W. Now we need to prove that the factorization is unique. Now assume that V is U1 plus W1, but it also U2 plus W2. What do we need to prove? We have the pair U1, W1 that works, but we also have the pair U2, W2 that works. But we wish to prove that there is a unique pair. So we wish to prove that it's the same pair. It's not really a different pair. The components are the same. These are like the blue forces. No, this is like the blue forces, This is like the green forces, and I wish to say there is no blue and green, it's all the same. Okay, it must be the same pair. Does anyone have any idea as to how from that data assumption we can prove that these pairs are the same?
I mean, assume by contradiction that they are different, and then we show that if U2 is different than U1, then W2 has to be different, but it will be a field kind of thing, like
I'll give you a hint as to the first step. We'll move these vector signs. Since we know U1 plus W1 equals U2 plus W2, we can say that U1 minus U2 equals W2 minus W1. Do you agree with that step? The left-hand side, at which vector space does it belong?
U.
U, because of closure, right? The right-hand side, but they are equal. What does that mean?
That they're in both, which means that it's not an exclusive sum.
Not exactly, because it's not an exclusive sum. They're within the intersection. It must be 0. Since both sides are the same vector, call it x, which is U1 minus U2, which is also W2 minus W1. Then x is within the intersection. Then, and therefore, x must equal the 0 vector. And what does it mean when it's the 0 vector?
But they're equal.
Yeah. And thus U1 equals U2 and W2 equals W1, just as we demanded. Okay. For the other direction, homework. Okay, if there is a unique pair, then it must be a direct sum. Nothing could be in the intersection, and try to do it as homework. Now we'll take our break until 2:30, and then we'll continue with the linear dependency and spans, not necessarily in that order. I'll start with span, I think. You can try. Yeah. The direction of everything.
Because the reason the resulting force is this way. And you cannot like do it together, you always know it's that.
Right.
There's also a resulting force from the object from the ramp on the car that way.
That's the normal force, I agree.
Yes, there is no force going this way, and there is no force going this way.
No, you're wrong. It's the
There is no
component.
force, the resulting force going this way.
Yeah, it's the components. It's two components.
No, but the components is this and this.
No. Gravity, not at all. The vector here is the normal force applied by the slope.
Yes.
But gravity is this and this. That's what gravity does.
Gravity is always down.
No, not all of gravity. Gravity also applies a force. What does the normal force, what makes the normal force happen? It's the third law that every force has every action has a reaction. So
Well,
what
okay, you're
happens?
decomposing gravity like this to calculate it separately, yes, but it doesn't.
What I'm
there
saying
no
is
actual
gravity
force.
definitely applies this force. And because it's applied this force, the car applies a force on the slope, then the force applies the normal force back.
Yes, but no, but there is no actual force like this. It's just decomposing the gravity in such a way that it's convenient. to
Yes,
calculate.
yes, but it's the same thing. That's the most brilliant part about it. There is no difference.
In part of
It is, and that's exactly what Newton says. Say, there is no difference between two forces and one force. Same thing. It has this very same effect. And mathematically, it's so important because it's like what you're trying to tell me is the 2 plus 3 is not 5.
No, but that's not what I'm saying.
But there are, if you say what forces, you can delete the blue forces and say the only force is gravity without the normal force. I agree. But you can say that these two forces are working on the same car. It's the same thing. Because the sum of these two forces is the one force you are talking about. I can't say it's only this force, it would be false.
No, it's not this force.
I mean this, well,
It's the what do you call it in English?
in which direction?
Up and left.
Up and here?
Yes.
That's the
It's-
normal force, but not by, that's not the force that the Earth is applying upon you.
It's not, no.
That's the normal force from the slope. But do you agree there is a force here? On that direction?
That's the result force from this to this.
This is the resulting force from?
From gravity and the normal.
No, before gravity, there is no normal force. The normal force does not stand by itself. It appears from the components of the gravity. And like I said, mathematically, the sum of the blue is equal to the black one. You cannot say I accept 5, but I don't accept that you say it's 2 plus 3. It's the same thing. And it's definitely the sum. Oh, it's true. In physics, I don't know, you probably won't talk about this blue component because in itself it does nothing, right? What you usually talk about, and I completely agree, is the normal force. But you're missing the step on how the normal force happens to be. And you can definitely not say that gravity is only this, right?
That's still being pedantic about physics.
Yes.
Well, oh, but I'm right here.
I choose my
I disagree, but I've decided that I don't care.
I choose my battles wisely. I don't fight up
Recent last year? No, you went to the cyber thing, right? Or women?
Okay. And the next subject is spans. So the next subject, right? Is well, the name is span, right? Which deals with what we can so-called create from a given set of vectors. What do I mean? If for instance, if I allow you to go east and go north, where can you get? I think we talked about it a bit with the New York cabins, right? It's the same thing, but now I'm going to formalize it. So if I allow you to go east, then go north, and I think the first idea people would say that I cover this second. Theoretically, it should not fail. I'll test it. Great. Okay. So I think that intuitively will you think about, I don't know, this like first quadrant, right? I can go where is this? North is there, I'm sure, and east is here in my direction. For you, it will be here. But you think only about this quadrant. But because we can multiply by negative numbers, since we can multiply by negative numbers, we can get everywhere on the plane. Okay, so that's the introduction, and now I wish to do formal definitions and theorems and all the math fun you love. Okay, so definition. Given a vector space V over the field F, and given a sequence of vectors V1, V2, Vn within V, we say that a vector V in V is a linear combination of the sequence. Basically, if I can get to it from this direction, if I'm able to think of it as points in the space, a point in the space would be a linear combination. If I can get to it from these direction vectors, this gives us the different directions I can go at. It could be n vector within an m-dimensional space. It could be a large space. But these are the directions I'm allowed to walk towards. And a vector V is called a linear combination of this sequence if I can get to it. And what does it mean, get to it? if there exists scalars C1 to Cn within the field, obviously, such that V is C1, V1, C and Vn. Okay, you see, I multiply each direction with a scalar. It could be negative, it could be larger than one, smaller than one. And then I sum them up. If I can get to V, then V is called a linear combination. Agreed? Let me give you a couple of examples. I'm doing it slowly for a reason. And if you ask some people, Thomas can do it, what is the stuff they find hard in linear algebra? They usually will say span and linear combination. Not for a good reason, just because it's a different language and it's hard to get, but it's not complicated. And so let's do a few examples. So say the vector space is R cubed and the field is the reals. The sequence would be V1 equals 1 to 3 and V2 equals 4, 5, 6. Agreed? Is 7, 8, 9 a linear combination of V1 and V2? What do you say?
Yeah.
I like Sammy because he said yes, and I said, yeah. Yes, yes. Wait, where am I? Oh, yes, yes. Yes. Okay. Why, Sammy?
Well, I was looking at it first. I was like, oh, you could just multiply. I was like, oh wait, you can't do that. It's 2v2 minus v1.
2v2 minus v1. I think you are correct. Right. Yes. 7, 8, 9 is actually 2 times v2 minus v1. So it is a linear combination of these two vectors. Agreed? How about 1, 2, 4? That a linear combination of 1, 2, 3, 4, 5, 6. Instead of guessing, let's solve a linear system of equations.
Let's
Our
take a
first,
shot.
our most fun game. That's why everything reduces eventually to matrices. Yeah, because every question you have a set of equation, you do in a matrix, and then you answer these type of questions. But my point is that what students remember usually is how to do Gauss elimination on the matrix, but they don't remember why are they doing it, and I think that's important to understand what is the question here and how do I get to the system of equations more than remembering to do Gauss elimination. In any case, let's do it. We're asking whether 1, 2, 3 could be C1 times V1 plus C2 times V2, right? And saying, putting a question mark because we're not sure, right? So two colors. And is there a solution for C1 and C2? That's the question. These are the variables of this system of equation. But now it looks like just like one equation. It is when I take it into, I separate it into each coordinate, then we'll get three equations. We'll do 1, 2, 3 equals C1 times 1, 2, 3. I said 1, 2, 3 equals 1, 2, 4 equals C1, 1, 2, 3, C2, 4, 5, 6. And we get the equation 1 equals C1 plus 4 C2. 2 equals 2C1 plus 5 C2. 4 equals 3C1 plus 6C2. Let's put in a matrix. The matrix will be 3 rows and columns C1, 2, 3, data. Okay, and we get here. Oh, I don't have a C3. Delete one column. So C1 is 1, the C2 is 4, 1, 2, 5, 2, 3, 6, 4. Do you agree? Now, let's solve it. And what is our question? Whether there is a solution. If we actually wish to find the scalars, meaning how long should we go, how far should we go in that direction, how far should we go in that direction, that's the thing that we will call coordinate, and we'll learn in the coordinates, and we'll learn about it in the future. Now we're just learning about linear combination. The question is whether there's a solution or not. Is there a contradiction line or not? Okay. So R2 minus 2R1 and R3 minus 3R1. And this gives us who would have thought entering into linear algebra course will give you post-traumatic stress?
Well, I mean, my mind erased it like a trauma.
So it's not your rate. It has also a name in psychology. It's called adhaka. Don't remember how it's called in English. It's when you internalize it until you forget, but when the right trigger comes, it comes back to you.
I think it's just one thing.
Maybe. Okay. So and 2 minus 2, that's 0. Next, and this minus 3. So that is 0. That is minus 6. And this is 1. And that, if you can notice, it does not look good. Last step. R3 minus
do another
2.
step after that.
Yeah, because I still didn't get a contradiction, right?
But it's quite obvious from that.
Yeah,
Like
quite obvious. Is his catchphrase.
no, because
Don't
The
skip
middle-
steps. Do the echelon form.
really
Do the echelon form. Contradiction. And there is no solution. Agreed? Why don't we solve this problem in general? What do I mean? XYZ is a linear combination of 1, 2, 3, 4, 5, 6, if and only if there exists a solution for, and I'll skip for the matrix because I just need to replace 1 to 4 with XYZ, right? It's the same, very same question. So I'll skip to that step. For this, right? Oh, sorry, XYZ. Agreed? Listen hard because what we're doing here is actually a tool, important algebraic tool that you use in the future. And you can look at the shorthand. The direction vectors are written in the columns of the matrix, and the variable vector, which represents a general vector in the space, is written as the a constant vector. And my question is, when is there a solution? Because when there is a solution, then it is a linear combination. When there is no solution, it's not a linear combination. And I would like to look at the set of all linear combination. That's actually is called the span of the vectors. It's the spanned vector space. Okay. So let's do this very same operations. That's why, by the way, I would have never done 1 to 4 like I did here. I always go XYZ because I don't know what next question they will ask me. So I'll do the most general thing. And it's the same work because I need to echelon Gauss eliminate these parts, and the XYZ are just there for the right. Okay, so it's R2 minus 2 times R1 and R3 minus 3 times R1, and we get and 2 times 0. 5 minus 8 is minus 3. Y minus 2 times X. Next. 3 minus X, 0. 3 minus 12. So whatever. Minus 6. Z minus 3X. Next. The step Semi did not wish to do. R3 minus 2 times R2. Here it's not obvious whether there is a contradiction or not, right? And we get here 0, 0, and here this minus 2 times this. So we get X minus 2Y plus Z. Agreed? So there is a solution if and only if. When does this matrix will have a solution?
X minus 2y plus z equals 0.
Exactly. Right? If it's not 0, then you have a contradiction line, contradiction row, and there is no solution. If it's 0, then that's an echelon form without a contradiction line. So it has a solution, at least one. It actually has exactly one because 2 variables are bounded, but I don't care about that right now. Agreed? Sammy, is your hand well connected? Impaired?
In pain.
In pain. No, that's okay. Impaired, it's not good. Pain.
It's okay.
Yeah, students in pain, it's the way you're supposed to be. More than that, physical pain is better. Sorry. Okay.
Rather than being in mental distress.
Yeah, exactly. Right. Okay. Try telling it to your parents. Say, oh, right, we've been telling you this the whole time. Okay, sorry. So the set of all X, Y, Z that are linear a linear combination of 1, 2, 3, 4, 5, 6 is all of the x, y, z such that x minus 2y plus c equals 0. Agreed? Let's go to GeoGebra. And write x minus 2y plus z equals 0. What do we see here?
Is it a plane?
No, it's Superman. Okay. I do have some new jokes due to English. Okay, because whatever. No, not again. Oh, just a second. It is a plane. It's not Superman.
It was a bird.
And I need to restart my do not save. Stop the share. What?
Ram, it says like Ram ran out or something.
I don't think so. I think it's stupid computers. I think it's exact terms. I think it has to do with GeoGebra and Zoom together because it's quite a powerful computer. It has 32 gigabytes of RAM and it's i9. So it's supposed to be, yes, it's a very good computer. That's why it's so fast. But I was disappointed when I had some problem with the GeoGebra because it pulls it down, and Zoom as well is not the best. I always think that's one of my students. That one of my students may have written the code that crashes behind it and say, should I release this memory? Ah, little memory leak never killed anyone. Doing restart and getting back. In computer, what?
There's a theory that essentially, as you go about life and you get technology, you gain or lose a certain amount of computer mana. And the more you have, the more, what do you say in English?
The more you have, the more affinity for computers.
The more the tech god likes you and the less issues you have.
Oh,
Did you read too much Warhammer 40k or something?
No, but it was theorized by specialized in one. Yes.
What a surprise.
I am a believer. God hates
The machine gun.
I wanted to say before that what Sammy said, what we learned today at school, that physical pain is better than an emotional one. And you're a best student because you understand it on day one. You need not
It's in the most
being told
psychological
that.
way.
So, but I do believe in technology mana in the sense that when you're young, you're willing to try everything and install that, install this. Then you get older, say, I just want a computer that works. That's how Apple was created. I don't care about installing stuff. I just want it to work. Will it work?
If you assure me it's going to work 100% of the time, I don't care.
Yeah, so that's Mac.
I don't care what deal with the devil it's signed.
Yes.
It's so frustrating. I like to tell the story is I used to use Arch and then I got the job.
You sympathize with. You sympathize. Also use right?
Yeah.
Okay.
But it was Windows. Yeah, like
Another funny thing is this computer is 3 years old
I don't know.
and it's getting a bit old and tired. I asked my the university to buy a new one, but you can only buy a new one once every 4 years. Okay, so I will 3 years.
So,
Yeah, but it's not working properly. So okay, next year I will have bugs all years because another year has not passed. Great solution,
you
guys.
can pay me to reinstall everything. Because I know you won't do it yourself. You don't want-
Yeah, but I don't believe in it. Installing everything is not. That's like Botox. It does not make you younger.
No, it's like juice cleansing.
Yeah.
I know what your computer needs. We'll just get it a pet rock that
Yeah,
like,
yeah.
gives it energy.
Yes. Put a
I mean-
plastic duck. Okay.
I'm not joking, I can't just reinstall it and clean.
No, I believe you, but it
And
won't
it-
clean anything. But
It will
one
work,
of the reasons is because I don't install anything.
it will work for a year. And you can get a new one.
No, it works not.
See? Like you don't. Need to pay
Okay,
me, bro.
never happened to me twice in a row.
It's
Oh,
it's you just lost like a bunch of tech mana, that's why.
just talking to you, I feel drain my mana.
Because I'm currently waiting.
No insult intended.
No, like
Some insult intended.
the irony is
Just insult intended. That should be a phrase. That's a true meaning, right?
the irony in all of this is that currently I'm writing a huge forum post on like a big tech issue that I'm having. So
Oh, I can't believe it. It's first time that it happens, and it happens more often. Oh, yeah.
My mana was drained when the army asked me for the 5th time in a row if I didn't mind being put on a closed space.
And
You
what
know
did
what?
you answer?
About being talking
I'm asking you for the 6th time. Yeah, girl, one time a girl in my class said, someone on the internet asked me a very bad question. It's like, and so what did you answer him? And she looked at me like, "Man, are you kidding me?" Just like Sammy did in a second, just a second ago. Okay.
Someone in 4chan asked me something very rude, and my first question was, "Why are you in 4chan?" And secondly, why do you care?
no, the first question should be, are you expecting something else?
Yeah, like, well, I mean that was what I meant.
Okay. Start. It will work.
They want you to go to B-Sides next year. B-Sides. Cybersecurity conference.
Whatever.
26th of June.
Where is it? They're not telling you. You need to find out for
It's-
yourself.
No, it's even worse. It's in Tel Aviv.
We're telling you, but there is no possibility to get there. Okay, I'm trying to open GeoGebra from the web site. Maybe it will not crash this time. So x minus 2y plus c equals 0. That's the plane here. And so far so good. And if I'll draw the two vectors which we started with 1, 2, 3. I actually wrote vectors. Vector 1, 2, 3, and vector 4, 5, 6. We do see these two vectors lie on that plane, and we actually solve something doing all of that. Anything else I wanted to say about Stan? Okay. Another example Oh, no, definition first and then example. Definition. And given a sequence V1 to Vn of vectors, the set of all linear combinations of these vectors is called span of V1 to Vn. Okay, it's the spanned space. Now I have an language question, because in Hebrew we call it span. We use the English word. So in Hebrew it's more confusing because people are not usually sure what span means. It's not used too much in English sentences. Can you give me a sentence with the word span?
Wingspan,
What?
wingspan, like a bird.
I didn't think about that. But then, that's just the length, right?
I mean,
so it's a bit confusing. What else?
You could say like a forest spans the whole, or not, really, but like the whole country.
It's more like a measurement, like a way of describing a measurement.
It's
That's
like
what's the span.
something being over a whole something, like like the desert spans the whole space.
Yeah.
Covers.
So I always say over the span of time, right?
Yeah, or that.
So in Hebrew it's nifras, which is it's connected to what you suggest, because nifras and mifras, it's the same thing, which is the span of the wings and the mifras of the ship. In any case, it's something that spans over. But if I put the quilt on someone, I tuck in my children. So I say tuck in, I would say cover. In Hebrew, you will say lifros tasnicha, to put it over, to span the quilt upon it. In any case, I think it's helpful to understand that this is the reason for the word span, because you have the different direction you can go over, and the span is everything, right? Wherever you can span your quilt or map over these directions, okay? So one linear combination is a point in space you can get to given using the given direction vectors. So what is the span? One linear combination is the point in space you can get to, but the span is
the line or the points.
is the set of all points you can get to. Agreed? That's the idea of span. It's the set of all points you can get to. In the last example, the span of 1, 2, 3, 4, 5, 6, we've proved it to be the plane of all points x, y, z, such that x minus 2y plus z equals 0. Agreed? This is the set of all points we can get to, and we see that it's a plane. I call this the geometric representation. And this the algebraic representation. I'm saying I'm calling it that because I call it that. It's not, I don't think there is a professional terms to these different representations. In high school, there is a name, they call this הצגה פרמטרית and this algebraic, but you need to be able to change representation. Why? If I ask whether the point does 1, 2, 4 belong to the space, belong to the space, in which representation is it easier to answer?
The right one.
On the right one, right? On the algebraic one. Like always, algebraic is easier on the calculation. The algebraic. You simply plug in the vector and you see whether the equation holds or not. Agreed? When I asked you this with the span and I did it before the break, you looked at me and you didn't know the answer, rightfully so, right? Because how can I guess whether I can get to a certain point? In the algebraic representation, it really isn't. What's the upside to the geometric representation? I can see the dimension very easy. I see two vectors, it's two-dimensional. I can see the directions it's going on. I can see more of the geometry. And the algebraic helped me solve things more easily. Sometimes we need that representation, sometimes we need that representation. Okay, agreed? And also I will say this is also the null space. Also, the algebraic representation is the null space we talked about. Look, this is basically the null space of the matrix of coefficients of the matrix 1, 1, 1. No, not 1, 1, 1, sorry. 1 minus 2, 1. Agreed? What's the solution to this linear equation? This time it's just 1. In general, the algebraic representation could be any solution to a number of equations. Okay, joint solution for a number of equations. So the algebraic representation is basically solution to the system of equations, which we talked about a lot up until now. The new thing we learned today is the geometric representation, the spans of the vectors. That's the new thing we started today. And like I said, because we wish to talk about dimension. And in order to define dimension, we will need to talk about the number of vector needed in the geometric representation. It's actually the minimal number of vectors needed, because you can add more unnecessary vectors that can be created from these two, but you cannot represent this subspace with only one vector. Any questions so far? Yes.
Find the geometric representation using the algebraic one?
That's the easy thing, and that's what we learn. Simply solve the equation.
No, that's getting algebraic.
No.
But the other way.
No. Getting the algebraic from the geometric is the hard part, which we did today. This is this. Getting from the algebraic to the geometric is what we did up until now in the course. It's just solving the equation, right? Because then you get T and S and you take them out and you get a span. Let's do it as an example, okay? Example. Example. Take the algebraic representation from before and convert it to geometric. So I take the matrix one, just copy it. I take the matrix, it's already in reduced echelon form. Y equals T, Z equals S, X equals 2 times T minus S. So the null space is all of the vectors of the type and of the form 2T minus S T S, such that T and S are real. Agreed? Just finding the general solution to a system of equations. And then we'll write it as T times 2, 1, 0 plus S times minus 1, 0, 1. Such that T and S are from the field. Any questions up until now? This should not be new. Now is the new thing. What is that? A scalar times a vector plus a scalar times a vector. What did we call it just now? No, I'm scrolling to show you that we just. It's that, right?
Yeah.
And what is that being called?
Linear combination.
A linear combination. This is simply a linear combination.
Sorry, Eris,
Yes.
where do you get TNS?
The what?
From where do you get TNS?
Here you find the free variables y and z, right? Because the pivot is here, 1. The free variables are y and z. So you can plug in parameters into the free variables, right? That's, by the way, we talked before about in calculus. I told you to solve question number 5, which we already started yesterday. And in linear algebra, I gave you to homework to solve systems of linear and equation. Remember?
No.
Let me make sure. So you obviously did not start it, but let me make sure that I did.
I'll start 2 days from tomorrow.
Yes. 2 days before the day after tomorrow. Such a long time ago. Look at all the fun we had together.
Which one is bigger, the linear or the infinite?
Which one is what?
The
Meaner?
bigger, the
Bigger?
one, the document.
Ah, the file, obviously.
Infinite.
Obviously the calculus, because we have 2 lessons. Sound like me. Sure I did, but I don't see it.
I never seen it in my life.
Yes. Yes, I should. Okay. It's not that I will give you now, it's quite something. Remember that I did told you. I'm looking for it not just for the I told you so, but also to copy the link easily instead of doing it.
Control find
That's a mess. But find what?
the
When I told them so.
no, the link to your website.
Yeah, but I'm not sure which link exactly. That's the main point.
Yeah, but the start.
There is a few. You think it will find a link within the.
Yeah, I can bet my ass that I think so.
Sure, how much that works.
Not a lot.
Okay. I don't find it. Math wiki. Not bad, but it's not this, but only one. It's written here, it's not a link within that. Ah, okay, maybe I was wrong. Could be. And note, before I finish the example, you should solve the following kind of questions that will appear on the exam. I told you this in calculus, and now I thought I told you in linear algebra. Perhaps I was wrong. In any case, I will tell you now. There is a few places to do it. I will give you. So question number 1 from this link. Question number 1 from this link. Thomas, look at it. So you won't say it. Never seen it in my life.
I've seen it.
And oh, now I cannot unseen it. And questions number 2 from that link. And wait a second. Because there are exams in the linear algebra, but they are less in frame than the ones I'm linking right now, when I can say all question number this and this, or on that and that subject. But on these courses, I do have this. So from this link, I'll just open it for you to see. Same. So question number 2 here, you see, here are 80 parameters. This is the linear system of equations. Find all for every value of the parameter, whether the solution has a unique solution, whether the system has a unique solution, infinite number of solutions, no solutions, and some kind of questions. Okay, so solve these kind of questions. We really did not do it for a long time, but you do need to know how to do it. Okay, and that's what I did here. And the summation was there. We do echelon form, we find the free variables, we plug in parameters into the free variables, and then we find the bounded variable. It was a long time ago. Okay, any question how I solve the system of equations? Then I got from this set to that one. And then I'm just noticing that this is a general linear combination. So this is the set of all linear combination. What is the set of all linear combination called? The set of all linear combination.
The span.
Span, exactly. That's the span of these two vectors, 2, 1, 0 and -1, 0, 1. So we went from the algebraic to the geometric. And I think something interesting about the metamorphose we did now is, if you remember, we started with span, we went to the algebraic representation, we went back to span, but we got a span of different vectors, right? So it may look confusing, but it makes sense. If I'll go to the GeoGebra and I'll plug in the new vectors we found, 2, 1, 0, and -1, 0, 1, vector -1, 0, 1, you can see that indeed all these vectors are within the same plane. We just found another geometric representation, and of the very same this is also annoying. Sometimes it does that. When I do print screen, it just brighten up all the colors. In any case, I was saying another geometric representation of the same subspace. What? Yeah. Yeah, I don't know why it does that. That's my mana being drained, like you say. And you're that falls, like I said. I was like quoting myself. Okay. For last example of this class, I like that it's on at the end of the class because it's kind of extracurricular. But we said that sound waves could be considered a part of the vector space of sound. And I would like to calculate the span of sine and cosine. So basically, there are two waves on the same frequency, the same note. It also has the same amplitude, but I don't think that matter much. And I want to know what is the span of these two. So again, if you thought about span geometrically as when we have direction, we span over all the space, here you cannot have a geometric representation of my question, but an algebraic one is great. So what would be the span and what kind of element would be in the span? Who cares to say? What's in a span?
All the points that we can get from.
That's true. So what do I write here? Yeah, exactly. I write A. A times sine x plus B times cosine of x. Agreed? Such that A and B are some real numbers. First step agreed?
Yeah.
Now let's do some magic. I don't remember if I shown you this magic specifically, but even if so, I'll write it again. Right, we use complex algebra, complex numbers. Right, A plus BI equals R cis theta. Every complex number we can write algebraically or geometrically. Therefore, the span is actually can be written in the following way. Instead of A, I write R cos theta times sine of x plus R sine theta times cosine of x, such that R is some big positive number, non-negative number, and theta is some angle between 0 and 2 pi. Agreed? Now, what is that? Can someone tell me what does that equal to?
It's the sine of theta plus x.
Exactly. Such that R is larger than 0 and theta is between this and that. And what's interesting about it, that's a general wave. That's a general wave. with some amplitude and some phase. Phase is where is the wave located. So basically what we've proven here, that for a certain frequency, we only need 2 waves in order to create all waves in this frequency. That means that every node is 2-dimensional. Okay, and we could not do that only with sine or cosine. We needed two vectors, 2 directions, and that has to do with the dimension. And just for general knowledge, has empirical repercussions. If we wish to record sound up to certain frequency, we have to double the speed of our sampling. Okay, it's not completely clear why, but it has to do with every node being 2-dimensional. So we have to have twice as much samples in order to find these frequencies. And something is called the Nyquist rule. Excuse me. And that's enough for today. And I'll see you in half an hour. Yes.
And that is a fine picture for me.
You know what it looks like? I need to find this name.
Started off well.
It was a guy who was selected in having this tracksuit standing